It occurs to me that if we're going to start recording this thing, I should hit record. All right, so
Yes.
let's start over real quick. Welcome to the pop quiz. We've had a few people venture a guess. We talked a little bit about what enumerate does with iterables. I think we can point to a few aspects of this, namely what's wrapping this is curly braces, not parentheses. So that would make it, as we discussed, a dict comprehension. And then enumerate is going to give us a list of indices for that iterable ABCD, the string. So we're saying C, but let's go through it anyway. Open up a REPL and should be a quick one. All right.
Syntax. Create. Huh.
I think I can make this a little bigger by doing that. Oh, I can't see the thing anymore. Oh, you know what? I think I can just do. Oh, there it is. Right? Yeah, I think that's it. And there we go. C. 5 points to Oscar. Good job, sir. All right, let's get this thing going.
And I put an alternate code in the chat quite some time ago, which will generate the same dictionary.
Yeah.
With,
that actually is I think the best
typing.
answer. That's the best answer because an alternate way to get the same result. That's very interesting.
Yeah, yeah, that demonstrates full comprehension of the problem set. Very good.
And a crazy ability to cheat.
Oh, you weren't supposed to admit the last part. I thought I'd throw in a meme real quick. Brought to you by Programmer Humor. All right, welcome everyone. It's June 6th, 2024. We haven't been in pandemic for quite some time, but we're still here on Zoom, which is awesome because we got people from all over. We've got a couple of Kiwis in here. We've got some people from out in the Bay. I'm in the Bay at the moment. Although a bunch of us were all in the same room just what was that, a week or two ago?
Yeah, I think last week, Wednesday.
Yeah, last Wednesday.
Yeah.
Did our first in person for the Python group in quite some time. It was great to see a lot of you in person. Taneem made it all the way out from the Bay, so that was cool. Thanks for joining. I wish we had, I don't know, more time maybe to play around on the turntables. I don't feel like I did enough of it to really get my head around any new feature, but thanks for hosting the after party, Nick. All right. Continuing to grow. I took a screenshot on this yesterday. I think someone left. I don't know what I did to offend him. We're back down to 1,736 members, but it's okay. When Robert and I picked this thing up back in January 2020, it was quite a bit fewer. I think we've added over 1,000 people since then. But thanks for handing it off to us, Josh. It's been fun. Still need to get you in here. We've been doing a pretty good job, so I don't think we need to read the SacTech code of conduct, but generally be cool, or I will be quick to remove you. But I should probably lock the meeting, huh? Isn't that that's like a thing? Yeah, I'll figure that out once we get going. Anyway, the meeting format's pretty general. We do the opposite of in-person meetings. We say, don't hold your questions till the end. We like to have the inline jumping off points to delve deeper into topics. Oh, wait, sorry, I said delve. I guess this must have been a script written by ChatGPT. But in any case, if you got a question, speak up. If you're feeling shy, don't worry. You can also drop your text in the chat. Or if you do want to talk but don't want to jump in, you can always raise your hand. But please be cognizant of what's going on when you are unmuted. No sound bombing, please. Most of the time I'll just mute you, but sometimes people are kind of jerks about it. I got a good feeling about tonight. So come chat with us. You can find us on Slack, our sort of quasi-parent organization, SacTech, is at sac-tech.com. You'll have to agree to that code of conduct that I had posted earlier in order to join the group, but get updates about SacPy and other tech-based groups in Sacramento. I also have a channel for SacPy in a Discord for my production company, Brazen Studios. You can find that at sacpy.org. Maybe I should get my head out of the way in case anyone wants to take a screenshot. We're also on Twitter. We tweeted earlier. Gotten a few speakers from tweeting. Hoping to get the pillow guy next. He was just on Mike Driscoll's Python show. We'll talk to Mike about that. Hey, Mike, set that up. Alex, come talk. We like pillow. Lots of funny memes on Reddit. Maybe not enough posting about SacPy. I tend to post the YouTube videos there after they're edited. I used to post links to the meetup group, but that's when we got a lot of crazy sound bombing. People demonstrating the latest Zoom hacks and stuff like that. That was always fun. Follow us on Facebook too. Go to group and a page. Sometimes I remember to put events up there. We're on LinkedIn too. Find us there. And most of all, subscribe on YouTube. Once this thing's edited, I'll update it there as well. A lot of good content. Has some pretty good, cool speakers in the past. As you can see, Python in a nutshell, folks. Travis Oliphant, the NumPy guy. More importantly, tonight we got Cameron. All right. I am going to drop the share, and this is the time I would like to invite everyone to turn on their camera and make the next Brady Bunch photo. So let me drop the share here. Twinkles, as always, front and center. Oh, James Powell wins best dressed by far. All right, everyone, smile, look intelligent, look off the camera, look into the lights. Nicely done. All right. So that's it for our intro today. Let's move on to the fun stuff. Reason for the season. Matplotlib and our very own Cameron Riddell. All right, so Cameron teaches this stuff and is a pretty polished presenter. We had some fun just looking at some of his content yesterday in the shakedown for this event. So really excited for this one. All right, Cameron, I'm going to hand the share off to you. So without further ado, take it away.
Awesome. Well, hello everyone. My name is Cameron Riddell. I do Python training for a living with my colleague here, James Powell. We do everything from intro all the way to advanced, including sessions on data visualization, which you're about to see, as well as scientific computing using everyone's favorite NumPy, pandas, polars, and more. Now, with today's talk, I wanted to revisit some of the things that I really enjoy talking about. That's going to be one, Matplotlib, which is my favorite data visualization tool, and two, some core concepts of data visualization. So while we're going to be seeing actually a lot of code today, I don't want to spend too long on the code. Instead, I want to use the code to articulate concepts to you all. But of course, I'm more than happy to discuss anything about the code or related to the specific code and Matplotlib examples. With that in mind, I'll go ahead and share my screen. So behind me, you'll see my screen. I'll head in the corner over here. And since I'm sharing a lot of data visualizations and I want you all to see them as crisply as possible, I'll even double share my screen. Before I dive into what we have prepared for today, I do want to ask, does anyone like Matplotlib? You can let me know in the chat if you actually like it or if it's just something that you have to use to make a data visualization in Python.
I kind of like it. I'm more of a power user than
Yeah,
than I guess a lot of people, but
it's
it does
one of
have
those.
its idiosyncrasies, so I'll
It
say that.
does. Whenever I talk about Matplotlib, I say there's always historical baggage, right? It's been around since 2002, 2003, or maybe in 2001, but they came over from the MATLAB world, hence the Mat and Matplotlib, and so they had this implicit global state API that people used, and then we kind of transitioned into using the OO worlds of Python, which is a much better interface, but then they had parallel, effectively, APIs for doing the same things, which ends up confusing a lot of new users. And so Matplotlib is one of the only data visualization tools that I've used where I'm 100% confident that it can do absolutely anything that I want it to do. So for an example, these are just a collection of data visualizations I've made over the last 12 or 15 or so months. I just want to show you all of the wild things that you can do. I don't know about you all, but sometimes in my free time, I enjoy recreating other famous data visualizations. So you might recognize Edward Tufte's New York City weather from 2003, as long as a couple of others here. But these were all done in Matplotlib. I used no third-party packages except for the occasional color encoding of text that you'll see. But other than that, pure Matplotlib, it's always got your back. Sometimes it can be a little bit of a headache, but once you learn it and figure it out, it's a phenomenal tool.
I'll
With
make
that being
the comment that they can improve shared, basically object state and multi-processing in Matplotlib a little better than what I found, unless there's something that's fundamentally changed in Matplotlib in the past few years.
Yeah, so you'll run into issues with multiprocessing, especially if you're using the pyplot.show or things like that, because it has to run its own graphical user interface with the event loop in the background, which typically, at least for multi-threaded programs, does not behave very well. If you've ever tried to run a tkinter app with multi-threaded questions or multi-threaded programming, it tends to be a headache because you end up getting tkinter wanting to be on the main loop, and you'd have to be very careful with how you spawn your threads. With that being said, let's go ahead and get started. And so talking about data visualization concepts, I always start with, why do we bother visualizing data in the first place? Oftentimes, right, we can look at a set of numbers, and we'll just dial in on a couple here. So these first two columns that I've shared. Now, I'll go ahead and print these out, and I'm sure many of us could look at maybe just the Y column, and you could quickly glean, the maximum is probably 10.84, the minimum is somewhere in the 4.26 on the 7th row index there. You could kind of guess at some statistics as well, but the reason we visualize data is because we almost are never dealing with two columns of 20 rows, right? We always have much larger data sets, whether that's more features or more rows. It's just something that us humans can't quickly look at and start to glean insights from. And what we end up relying on are aggregations, right? And so here I have the mean of the X column from dataset 1 through 4, as well as the standard deviation for the X and Ys from dataset 1 through 4 as well. And if you look across these rows here, I should say across these columns, you'll see that they all have the same mean for the X's, they all have the same standard mean for the Ys, and they all have the same standard deviation for the X's and the Ys as well. And so if all we do is rely on summary statistics, you're often going to be misled. And the reason that you're going to be misled is once we actually go ahead and plot these data sets against one another, these X and Y pairings against one another, we can quickly start to see that these all look quite different. Now, I can go ahead and I can actually further add on a couple of other features here. I can calculate a linear regression and I can add that onto the charts, right, using Matplotlib's AX line, which is a fairly recent addition. I want to say 3.7 or newer in Matplotlib, is effectively like a line that's going to span my entire axes as opposed to one that's going to be bounded by some data values here. I can also go ahead and I can recompute those statistics that you saw, the mean, the standard deviation. I can give you the correlation coefficient, and I could report the slope here as well. And if we take another peek at our visualization, we'll see that we have our slope there, as well as those reported statistics. Now, if you look at those reported statistics, you'll see the summary stats all look the same, right? And these are just on our Y values for the summary stats there. And so if you never visualize this, you would be led to a false assumption about what these data sets all look like and how they might be related to one another. And so the reason that we visualize data in the first place is to offset cognitive load, right? We don't want to come to incorrect conclusions, especially when we rely on just summaries of the data. Data visualization is the only way that us humans can actually understand and ingest hundreds or thousands of data points at once and start to pick out relationships. So now that we know why we would visualize data in the first place, when should we do it? Well, there are two reasons that I often refer to. One is exploratory and the other is communicative. An exploratory chart, this is something you'll likely reach to like a tool like Seaborn for, right? You might make a facet grid, you might look at multiple features plotted against one another just to understand what your data set looks like. You also might make like a histogram of every single one of your columns or every single one of your features in order to understand what those data points look like without being related to any other features in your data set. Now, a communicative chart this is what we'll focus on for a large portion today, because I think this is the most interesting type of chart that you can make. It's the chart that articulates a specific point. This is the type of chart that you'll make when you create a report and you hand that into your boss. Or if you're an academic researcher, this is the type of chart that you would create to send in for a publication because it highlights the main point of your work. And so our communicative charts are there to communicate findings of an analysis or investigation or to justify a decision or even its reasoning. And so when I talk about communicative charts, well, I always think of what is it that I'm trying to say? You're almost always trying to communicate a specific message. And that leads you to a further question, one more removed, as what is a message? Well, a message is comprised of two pieces or two parts, one part signal and one part noise. And what we're trying to do whenever we communicate, whether it's through data visualization or just talking in a room, we want to maximize the signal and we want to minimize the noise. Having a high signal to noise ratio means that you are going to be heard. So if I'm speaking to you in a room and there's nobody else in the room and I'm just standing maybe 5 feet away from you, even if I speak quietly, you can probably hear me. Even if the signal's low, in the absence of noise, there's a good chance that you'll be able to understand my message. Now, if you add in noise, if we crowd the room with 100 other people and I'm still speaking quietly, that noise will drown out the signal. And so what I can do, I have two options. I can project my voice, aka increase my signal, or I can start asking everyone who's entered the room to leave. I can decrease the noise. So those are the two focuses that we'll have for increasing the clarity of our message.
Now, to that end, with respect to noise management, there was a question a few minutes ago from your colleague. How much grief are you willing to accept during this presentation in the form of inline questions?
Inline questions, either raise your hand in Zoom or just throw it in the chat and I can respond to it verbally.
Okay, cool.
Awesome. Okay, so now that we've talked about what a message is, let's talk about how we can communicate visually. What are our options here? And before we jump into the different types of charts, right, a box plot, a bar plot, etc., let's talk about something simpler. What are the visual channels that we can encode information in? These might seem a little simplistic on the surface, but you can encode visual information through the position of different points, through the length of lines or of bars, through angle, slope, area, volume, density, and color. These are all different, valid, and usable channels that we can communicate information through visibly. Now, it turns out that these are not all created the same. And what that means is we're talking about human perception, specifically visual perception. And as far as human perception is concerned, right, these aren't all the same. Not every channel is created equally. And so what we need to think about is how human perception affects our ability to perceive information visually. But taking one step back from visual information, let's look at what is referred to as Stevens' power law. This is human perception here. So there's a number of different experiments, and these have been replicated a few times across noiseless environments. I will give that caveat, but the crux of it is this. If we were to take each of these stimuli, we have an electric shock, saturation, that's visual again, visual angle like we just saw, length, visual area, and brightness. Turns out that a 1 unit change in the physical magnitude, that is the objective magnitude of the stimulus, is not perceived as the same unit change for the perceived magnitude. And in fact, each one of these stimuli follow a different power law. And so the electric shock, if you take a zoom in on the electric shock here, as I've highlighted, and we were to ramp up the strength, I will say this, I have a background in psychology. The electric shock is almost always delivered just by electric pulses to your fingertips. So it's not gonna hurt, but they do ask you to report how much it hurt, right? Or how intense was the sensation. So if we take a normed physical magnitude of 0.5 and then we ramp that up to a 0.6, you can see that the perceived magnitude doesn't change too drastically. And so at low strengths or low signal strengths, there's actually not much of a difference in perception. However, once we cross a fictional magnitude of about 1, right, a small change, that same 0.1 unit change, draws or elicits a massive perceived magnitude. And all this is going to say is that 1, an electrical shock is not a good way to reliably communicate information to a person, but 2, when we are trying to articulate something, whether that's a message or anything we want to communicate, we want to use something that has a one-to-one relationship between the physical magnitude, aka what I say, and the perceived magnitude, aka what you hear or what you perceive. And so this is when we might want to use something that's a little bit more reliable. So I'll go ahead and we'll highlight just another one of these entities here, the visual length. Turns out that as far as visual length is concerned, as we've highlighted here, there is always a one-to-one relationship. So any small change in the physical magnitude is represented perfectly by a change in the perceived magnitude. What this goes to say is, if you show me 2 lines where one is a different length than another, I can quantitatively describe to you or estimate to you how large that change is. No matter if that change was small or if that change was large, if both lines started off as short and then both lines became large, I can always tell you a reliable metric of how significant that change was. That's what our human perceptive system is good at doing. Now, this chart is not to say that things like visual angle or color saturation or visual area brightness are bad to use. It's just that they are not as reliable as communicating information via visual length. And so, going back to all those different channels that we saw earlier, we can actually rank them. And this isn't something that I have done. This is something that John McInlay did in, I believe, the 70s or the 80s. And so looking at quantitative perceptual tasks, humans are more accurate when it comes to making judgments about changes in position, like you would use for having non-overlapping bars on a bar chart, or changes in position between 2 scatter markers. If I shrink the distance between them or grow the distance between them, you can very accurately tell me what that difference is. And same with the length, as we've just talked about, right? With bar charts or with line charts, I can tell you if one bar is longer than another. Where we get weaker and weaker is with things like angle or slope. Although large differences are obvious, and I bet you can tell me that there is a difference between the 2 angles in that angle chart right there. What I'm willing to bet, what you can't tell me, is quantitatively what that difference is. And same thing all the way down with the color. If you can give me a quantitative measure of how different those colors are, I'll be very impressed, and you might do something with color for a living. And so when we think about these perceptual channels, position and length are always going to be some of our most reliable ones. Then going all the way down, density and color, although they can tell us that a difference is present, it is hard for people to quantify what that difference is. And so with that all set, now we can talk about what charts people will commonly use. My first focus here will be on univariate charts, so just plotting a single feature. So there are a number of different ways that we can plot a single feature. In fact, I'll show you that 2 that are built into a tool that you all might be familiar with, Seaborn. If we look at the strip plot and the swarm plot, we can actually see what the density of the data is. And to describe this chart for you, I have 4 different populations. From these populations, I drew 100 random points. I then plotted those 100 points from that sample. Now, the strip chart is effectively, you randomly jitter the points along a y-axis, but you reliably encode their positional information along the x. And so what you're looking for here is a measure of density. How close are the points to one another? Now, the most obvious one here is going to be the skew norm chart, the third column. You can see that the points are most densely focused around the highest probability density of our population, which makes sense because we drew 100 points from that population. However, I wouldn't say that the density is very easy to see, especially with how much we've jittered the y-axis. If we were to decrease the jitter along the y-axis, it might be a little more obvious. Another way of presenting these same data are using a swarm chart, right? A swarm chart is going to reduce the amount of jittering along the y-axis and keep the points a little bit more close to one another, and you can kind of glean the same observations here. One important thing to note, though, is that what we have done here is we have encoded the density of these points using position, right? Just like we were talking about. So how else can we represent this information? Well, I don't actually have to use a scatter marker at all. And by not using a scatter marker, I'm actually free from having to do any jittering along the y-axis. This is called a rug chart. And now instead of scatter markers, I'm just using vertical lines. Again, you're looking at the position here. How far apart is each vertical line from one another in order to determine where the highest density of your data exists. So those are three ways that we can use position. But what about our other measures, right? We can use height, aka our length here, as well as color. So I'll show you two kernel density estimates, one using area and the other using color intensity to highlight the densest areas of our sampling. And so the kernel density area charts is using height to convey more points have fallen in this area rather than that area. And the color estimate is using color to convey the same information. One thing I always say when I share this chart is that be careful when you use kernel density estimates, since you're applying a Gaussian or convolving a Gaussian curve on top of your data, you are going to end up with, unless you're careful, end up with estimates that don't actually reflect where real data points are ever observed. Take the triangular distribution on the far right. You can see that my kernel density estimate is not clipped here when it should be clipped.
Oh, I'd like to point out, how many points did you use in generating the sampling from the distributions? Was it 100 or 200?
So there were 100 points sampled from the parent distribution.
Okay. Yes, I deal with a lot of KDEs, and they can be powerful, but they can also give you they'll have problems themselves, as you see here.
Yeah, they can definitely have problems, and it can also show you distributions that aren't actually there, especially since you're smoothing the data, right? Look at how Gaussian, right, the triangular distribution ends up looking. And the skew norm almost looks like there's two separate distributions that fuse into one here as well. And then a uniform is, I mean, that's not what the uniform distribution looks like up there. So a couple of other approaches that we can take are to use cumulative density functions. Now, cumulative density function, I am a big fan of, but if this is your first time seeing cumulative density function, it might feel a little bit different than what you're used to seeing. And so for the cumulative density function, all you're looking for, whether you use a convolved one with a kernel density estimate or just a raw empirical cumulative density function, anywhere you see a sharp increase in slope, that's where there's going to be a lot of data points, all closely and tightly compacted around one another. So take that skew norm where we have a large probability density under effectively the median, right? We have a very intense slope because that's where most of the data fall. Wherever we see a flat slope, that's where less of the data end up falling. And whenever we see a very continuous change or a continuous slope, right? One that doesn't change, you can assume that there is no specific mode or mode to the specific sampling that you've done. Now, I'm just going to go ahead and uncomment the rest of these because there's so many different ways that you can plot univariate charts, but we can take a look at histograms, which are probably one of the most common, which will also skew. I could probably do a whole slide just on histograms and how to calculate the number of bins. There's a ton of different approaches here, but there's also box plots, boxen plots. Tufte came out with his own type of quartile plot, which is very minimalistic in the Tufte style. But all of these are being used to convey the same type of information. How many data points fall into a particular space, and how can I communicate that to someone? And so no matter what chart you end up choosing, just know that the differences between these charts are the channels in which they encode information, as well as how they aggregate that information. Take the histogram, for example, you have to do some binning and then some counting. But after that, you use height to communicate the density of the points. but that's plenty of univariate charts there. So let's talk about visualizing more than one variable, aka relationships here. And so this is actually straight from the Matplotlib documentation page, or I should say tutorials. This is not an exhaustive list by any means, and these are probably the charts that everyone here is going to be familiar with, right? A line chart, scatter, bar. Stem charts are, they tried to make an appearance like in 2020, 2021. They were big on like iconographs and things like that. Or sorry, infographs, not iconographs. And I don't think they really landed too well, in my opinion. But you also have step plots, area between area, which is really just a play on an area chart. It's used to typically show error or an error band. And then finally a stacked or a singular area chart, which communicates very similar information as to a bar chart, but the underlying metric is not categorical, it'd be continuous. So these are just some of the ways that you can communicate relationships. We'll get more into each of those specifics, but before we do that, let's take a peek at what if we have 3 dimensions, right? These types of charts are often for 3 independent or 3 related variables. So you can think our matrix, you have an X and Y coordinate or a grid system, and then you have a Z axis, maybe the intensity of something or maybe the height of something. There are stream and we have our contour charts. If you've done any hiking and you use all trails, right, you've probably seen a contour chart to communicate latitude and longitude as well as the degree of elevation. You can also use contour charts to, if you have a very dense scatter chart, you can use contour charts to communicate information about the density of those points. We'll talk more about scatter charts and overplotting later. You can use choropleth if you have true Latin long, right, and you're trying to represent geographical boundaries, and then finally quiver plots if you're into physics. So if those are some of the ways that we can represent 3 variables that are all separate from one another, oftentimes I work with individuals who have 2 or more variables that they want to visualize. And sometimes those dimensions or those variables are a subset of one another. And so take this chart that we have here, for example. In this chart, I'm articulating that I have a fake or an imaginative restaurant. And every day, customers come into my restaurant. And so I've plotted that daily data over time. Now, I have 10 years worth here of data spanning from 2000 all the way to 2010. And the whole point of this chart that I'm trying to communicate is from 2000 to 2010, my restaurant received more and more customers year over year. Now, what we've done to communicate 3 dimensions here is we have an X and Y, right? The number of customers as well as the month. And then our color is actually a paternal or a parental dimension, right? A hierarchical dimension to the month. It is the year. And so we have technically a 3rd dimension here that's represented by color. So we're using color as a 3rd channel. Now, this is one of those charts where you look at it and you have to look at it for probably about 10 or 15 seconds before you realize, oh, the darkest color is the year 2000 and the brightest yellow is 2010. I can very clearly see a shift or a change in trend over time, right? So I don't think color is probably the best way to represent the year if our message here is to articulate that daily customers increase over time. Instead, what we might reach for is one of my favorite tricks, right? Instead of relying on color, we can reuse position. And what I mean by that is we can use a trick called small multiples. Now in our small multiples, what you can more clearly see than you could before is I have a small chart, 1 chart per year for the past, from 2000 to 2010. I have plotted all of the data on every single chart. This facilitates comparison, specifically a one-to-many comparison. Take the top left chart, the year 2000, for example. In blue, I have highlighted the data for that year. In gray, I have shown you all the data for all the rest of the years. So you can quickly look at that chart and you can tell how many customers did I have in the year 2000 compared to every other year. Now the red line there is to represent the average number of customers across that year. And what you can see is that pattern of the red line increases every single year when you look from chart to chart. So not only can you take any one of these charts and gain something insightful, but you can look at the pattern across them and also understand that my daily number of customers has increased over the years, just like my title says. And so You can do this in a tool. Small multiples is very easy to do in a tool like ggplot or plot9 or Seaborn as well. And if you want to use a little bit of Matplotlib, you have to do a little bit of math here, right, to calculate all the number of different axes that you need to plot on each of them. But I really like the formulation that Matplotlib gives you because it gives you an almost unlimited amount of control over where things appear on a chart and where your charts appear on the figure or your metaphorical sheet of paper. And so if you do have questions about the code, I'm more than happy to discuss the code in the chat. But let's go ahead and talk about colors. How do we use colors? What makes one color palette more appropriate than another? And so let's take a look here at one of our options that we have. This is a heat map. A heat map is used in this case to represent Pearson R correlation coefficients. So I have time series data. I correlated temperature of outdoor temperature from some synthetic data set to ice cream sales. And you can see that there is a positive correlation between temperature and ice cream sales. Hopefully there is. Now, tech stock and finance stock is not correlated with temperature, but without a color bar, I have no idea what green means in terms of correlation. So I can intuit, right? Red might be a high or a positive correlation. Blue might be a low correlation, but where does green fall in the middle? And how in the middle is it? Of course, we can alleviate this concern by adding a color bar, right? And if I add the color bar, it becomes a little bit more obvious. But what I strongly dislike, and this is the jet color palette. So if you've ever heard about the jet color palette, you know it's not a great choice. Or if you've ever programmed in MATLAB circa 2013, you'll know that this was the default choice in MATLAB and led to a lot of very distracting charts. And I'll say distracting because the issue with the jet color palette is that the intensity of the luminance in the green and the yellow is higher than that of either endpoint, the red and the blue. And one thing that we really like in what are called our sequential color palettes, that are our color palettes for continuous data, is that they start on one low luminance end and then they move to a higher luminance end. This is true for our sequential color palettes that expand in one direction. Now, a sequential color palette is not going to be the best choice for a heat map, specifically one where you're articulating correlation coefficients, because correlation coefficients are bound by -1 and +1, and they have an inflection point in the middle. That inflection point is indicative of a positive or a negative correlation. And so, what we would do instead is reach for a diverging color palette, one that inflects just like the data do around 0. And so what you can look at from this graph is 1, your eyes are almost already drawn towards the dark shades of blue and the darker shades of red. This is because they don't fade into the background, they stand out more. Typically, if you're communicating correlation coefficients, the high magnitude things, whether it's positive or negative, are going to be the things of interest. However, or in addition, I will say, is that even for the weak correlation coefficients, this light blue, even though it is a very, very pale blue, I can tell that that's a weak positive correlation because it is slightly blue, right? Whereas with the chart, the jet color palette on the left, this green, I couldn't tell you if that's a positive or a negative correlation. I can tell you it's somewhere around 0, but I couldn't tell you which way it's leaning. With a diverging color palette, it's much more obvious for both strong and weak correlations. So that's how we can use color effectively. There are probably a million more examples we could draw from, but I want to talk about revisiting our signal to noise ratio and how we can communicate a specific message. The most obvious thing that we can do is increase our signal, right? Just like the example where I was talking to you in a room, the easiest thing I could do is to project my voice more. And so how do we do this visually? Well, the most obvious, or probably the easiest thing that we can do, the thing that I don't see happen very often, is we put the bottom line up front. And what do I mean by bottom line up front? Well, take a look at this chart here. On the y-axis, we have cities. On the x-axis, we have temperatures. And my title just says temperature by city. You could look at that title and then you can look at the y-axis, you can look at the x-axis, and it feels redundant. I know that this chart is temperatures in cities. You don't need to tell me that in the title. Instead, what you should do with any good title, you should pick a point or pick a narrative from your data, assert that point, and then let the chart back up your point. So I can change the title to LA has the hottest weather on record for whatever fake data I decide to create up for this session. But the important part is this. This title is a reflection of the data. I am not saying anything outlandish or anything uncircumstantiated by the data. I'm not saying global warming has made everything hot, because that's not what this chart represents. This chart has temperature from 5 or 6 different cities, right? And so make sure that whatever claim you make, you can actually back up with the underlying visualization. Now, I always liken the bottom line, and I'll bring the chart back up. I always liken putting the bottom line up front to 2 things. One, if you have ever if you've ever baked or cooked and you have tried to find a recipe online and you end up stumbling onto someone's blog post, does it feel really annoying or tedious to have to read through like 8 pages of that person's life story about how their grandmother came up with this recipe and they grew up, together, baking together, and how much fun it's always been? And you're just like, look, I just want the recipe. And you have to scroll all the way past it. That's what we're trying to avoid with our chart. The other example is if you've ever read an email that asks you about how you're doing and then tells you about their day, and then at the very bottom finally asks you the question that they were emailing you for, put the bottom line up front, right? Save us a little bit of work, save us a lot of digging, and just make your title your assertion and let your chart back it up. The next thing that we can do in terms of increasing signal or boosting signal strength is to use a trick that I call redundant encoding. And one of my favorite examples of redundant encoding, we're actually going to go back to our example that we saw with our heat map. Now, if I show you this heat map, what I've done, I'm using position, sure. I'm using position to articulate, right, the categorical differences between my features. But the important one, the thing I want you to focus on is I'm using color here to represent the magnitude of that correlation coefficient. What if I were to also redundantly encode the correlation coefficient in size as well? You can already tell that your eyes are immediately shunted away from the areas of low magnitude or low correlation coefficient and drawn to the interesting areas, the areas of high correlation coefficient. And since I've doubly encoded this chart, I will argue, does this even better than the above chart, which only uses this single channel of color. But the story does not end there. We can take this one step further. And I can do that by completely changing the chart type. I can triply encode the same piece of information through color, through length, and through position. Position here is communicating, right, the same story as it was, the comparisons, but now instead of using size, which is not as reliable as length here, I'm using length to articulate, right, the intensity, the same information as the color, and then I'm using position in a way I couldn't do before. I'm using position here because I've sorted these bars. There is no sorting in our correlation matrix, right? The heat map that we saw earlier. With a bar chart, you can sort from a high positive magnitude to a low magnitude. And so now you can very easily see the high areas, the areas of high magnitude that you're more likely to be interested in, and you can easily rank them without having to do very small color differences. Take this experiment, for example. Look at the correlation coefficient between ice cream sales and temperature, as well as people swimming and temperature. It's very hard to see this very subtle difference in shade of blue. Additionally, it's almost impossible to tell what is the magnitude of that coefficient, right? Is it 0.6? Is it 0.7? I can't tell you with high reliability. Now, take the bar chart. I can more readily go across my x-axis and visually look up and tell that it's about 0.7 in terms of correlation coefficient. And because of the positional ranking, I can tell you that the that the temperature in ice cream sales is a stronger correlation than ice cream sales and people swimming. And so these are the types of observations that you can glean from using or thinking about the types of channels in which you can encode information in. And now that we've talked about ways that we can boost signal, because there's a lot of them, let's talk about reducing noise. How do we reduce the noise in our charts as well? Well, the first thing that I want to consider when talking about noisy charts is overplotting. Now, overplotting is something that happens whenever you're working with a large data set. This is more likely than not to happen. Overplotting happens right when you just have too much data to present. Your first instinct might be, oh, well, I need to aggregate and then report some measure of spread or error. But the first thing that you could do is you could just plot, if I have two clouds of data here, you just plot them on different charts. And this is a fine solution. However, if I want to compare these two groups to one another, this becomes very hard because I have to start glancing back and forth between these charts. Even with the shared X and Y axes, it's simply not easy to do. Well, what if I superimposed? And so just for some vocabulary, juxtaposition or juxtaposing is when we take two groups of the same data set and we display them on different charts. Superimposition is when we overlay them onto the same simple chart. However, this brings up an issue in terms of our data presentation. And I'm sure you all can already see it, but we have an issue here called occlusion, meaning the orange points are on top of the blue points. I can't tell you how many blue points are under those orange points. We even had this issue with occlusion before with the juxtaposition because there's just so many blue points and so many orange points independently that it's just hard to tell what's going on in this data. How dense, how many points are there in the orange cloud? How many points are there in the blue cloud? I have absolutely no way of telling. So occlusion here is our representation of overlapping features or overlapping data. Now, the next thing that you might reach for is once you acknowledge, okay, there's a lot of overlapping points, maybe I just need to make everything more transparent, right? And this is when we start using that alpha level or that transparency level in order to blend the data points on our charts or have them blend to the background. While I can see where the highest density areas are respective to the lower density areas, we have introduced yet a new type of error. And this is called washout. And the whole point or the whole story behind washout is that, well, some of these points are so transparent and there's not enough overlapping points for them to actually accumulate opacity to a high enough degree where I can actually see it. So these points just fade into the background, right? They're washed out. The other issue that arises when you use and just use the alpha or the transparency here, that should not be occlusion. This is oversaturation. So I'll go ahead and fix that for us. It's oversaturation. When I look at these points here highlighted in the oversaturation, is it blue? Is it orange? It looks brown, right? It's just somewhere in the middle. So these are very common problems when it comes to overplotting. Now, another solution or another solution that you might arrive at when you're taking this journey down overplotting is to use not alpha, but you might actually just change the size of the scatter markers, right? And by decreasing their size and maybe getting rid of the white edge color that's around all of them, well, now we can see a little bit more of the data, right? We can tell where these orange and blues are not as overlapping as they could be, but we still have that same problem of occlusion, right? And now since we don't have the white edge color, these points just blend in to one another. And so I think if you've gone down this path or this journey before, as many of us have, you end up on some type of solution revolving around make things less transparent or make things more transparent and decrease the size of the scatter markers. And you'll probably sit there like I do and you say, okay, let's try alpha 0.8, size 30. Okay, alpha 0.7, size 26. And you sit there and you keep repeating this kind of loop. And this works, right? Because you can eventually get to a chart that has a low enough level of washout, as well as a low enough level of occlusion and a low enough level of oversaturation, where you can actually see the cloud of data points. This is great if you have to do it once. As soon as you have to do this many, many times, it becomes a big pain. And if you think in terms of our visually communicative channels, you might come to a different solution, a completely different interpretation of how to approach this problem, and that is to use something like a 2D histogram. I've re-encoded color. I'm no longer using color to translate or transfer information about groups. I'm instead using color to translate information about the number of data points that fall into a small gridded area onto this chart. And here you can really see, you can actually quantify the density of these clouds of data. You can even juxtapose these two parts to show what they look like independent of one another. Now, an issue comes where you think, well, now I need to figure out what's the orange group and what's the blue group. We could use some labels, or if you juxtapose them, of course, you can label the charts themselves. So I won't say that a 2D histogram is going to be the best solution, but it is a solution. It's one that you can readily come to when you start thinking about encoding visual information in channels instead of scatter charts and 2D histograms. Now, the last solution, this is a for fun one. This is using Data Shader, which is a tool put out by the folk over at Anaconda who make panel, HV plot, hollow views, etc. And so Data Shader is designed to automate some of this. I have a huge data set problem and I need to reliably communicate that information. And so effectively what the algorithm does is it automatically chooses some combination of alpha and size, as you can see here, and it does some aggregation for you as well, spatial-based aggregation. And you can see that with no added inputs, I actually get a chart that looks quite nice and does convey information about the density of these points. I will say that the algorithm can be a little slow, but if you're looking for an automated tool, something that can solve this overplotting problem for you, it's a great place to start. There are other approaches, other tools that you can use as well. Now, also on the same realm of decreasing noise, right, to increase that signal to noise or increase the strength of our message, we can also think about chart junk. Now, this is coined by Edward Tufte, who is kind of like the OG data visualization or visual information communication expert. And so the idea goes like this. Of all the ink on your chart or all of the pixels on your Matplotlib figure, right, how much is actually being used to represent data and how much is being used to represent supporting annotations that are actually not beneficial or do not actually highlight the data. And so you might see some charts that look like this. And this is a slight exaggeration, I will say. But if we take the temperatures in our city, this time Austin's the hottest, we decided to change which city's the hottest. But taking a look at this chart, I got my bottom line up front, that's great. However, I have a lot of distracting features here. And the first distracting feature that I want to orient you to is actually not what you're going to think it is. It's not the grids and it's not the ticks. It's actually the X and Y labels themselves. If you are an American citizen, and if I'm telling you about temperatures from cities in the US, I'm probably telling US citizens about these data. And so you might think, well, if I see Austin, Los Angeles, San Francisco, Baltimore, Chicago, New York City, I know that these are cities. So why do I need a Y label there telling me that these are cities? It's like a reminder that's just silly. An even worse case than this is whenever you see a chart that has an x-axis and it's like January 2000 to December of 2010, and along the way there's different years, and then at the bottom it just says time. You're like, I know it's time. It's so obvious. You don't need to put that there. And so if it's a redundant label or if it's a label that's already articulated by the data themselves, you don't need it. Now, another trick that we can do, speaking about the labels, is looking at the temperatures down here. I have 0, 20, 40, 60, 80. And then below that, I put temperatures and in parentheses, degrees Fahrenheit. I can actually get rid of the word temperature completely. And I can do that if I put my measure, degrees Fahrenheit, next to every number on my x-axis. And so if my chart looks like this now, I can get rid of city because it's a redundant or an unnecessary Y label. I can get rid of temperature as well as my X label too, and I can do what's called inlining my measure. And so I inlined the label, the degree Fahrenheit, into the actual data labels along my X-axis. If you see 0 degrees F, you know that we're talking about temperature or heat in this case. Now, the next item, the next thing that we can clean up on this chart is probably the most obvious, right? It's going to be that incredibly intrusive grid, as well as the very large tick markers, as well as, I will even say this, the rectangle or the box spanning the entire chart. So I'm going to show you what this chart looks like now. I'm going to remove those features and look at how less distracting this chart is. I have done one thing though. I've added what's called an invisible grid. And this is going along, I should say it's along the x-axis, but it's parallel to the y-axis. This is a Tuftean idea. I'm not super keen on the invisible grid. I personally don't like it, but I think we are at a point right now where personal taste does come into account. And so what Tufte's idea here with the invisible grid was, yes, I can look at these bars and I can tell how long they are. I can compare their lengths. I can do that very easily. What the invisible grid enables me to do is actually count the number of segments between the bars. However, one thing that I don't like, if you are familiar with visual illusions, you might start to notice out of the corners of your eyes little gray boxes appearing at the intersections of each of these rectangular boxes. And so that's one thing that I don't like. It is an optical illusion that's introduced by the invisible grid. I could alleviate that by using a different background color, which is a very common trick to do, or I could just not use the invisible grid trick. The final thing that we can do, and we'll see if you can tell the difference from what was before, but I can actually remove the x-axis completely. And I can do that by taking that inlining trick where I put my X label into the X ticks. I can actually do that again, and I can put my X ticks, I can do away with those and just inline my actual data. The x-axis is still there, it's just invisible. It is still a stick of measurement. However, I'm now communicating the exact precise data that each of these bars represent. And so when I do this, I don't really need an x-axis. I will say that this trick is not something that you'll see in many academic publications. However, this is a trick, if you look at charts from The Economist in your spare time like I do, this is a trick that you'll see all the time in there for just really maximizing that data to ink ratio, just removing axes completely because they're unneeded and they are articulated by the data themselves. And so that's just a couple of ways that we can eliminate chart junk. The next thing that I want to talk about in terms of reducing noise, actually, I will say that this falls under both, reducing noise and increasing signal. It's intentionality. I've seen so many charts that look exactly like this. And now before I get to this chart, I want to show you what the data look like, right? So I'll go ahead and we'll print out just the first 5 rows of this data frame that I've constructed here. And I'll tell you that these are revenues per month from different regions of a mega corporation that I own. Now, you can see here that these are actually millions of dollars. So this company here made about $10,000 million. Maybe I'm exaggerating a little too much here, but the story goes like this. I received this data set and my boss said, show me the data. And I say, you know what? I can show you the data. Now I've used Matplotlib here, but you can see I'm using pandas.plot, which is one of the simplest interfaces we have in terms of putting data on the screen. I could also use Seaborn cat plot for what I'm about to show you, or a Seaborn bar plots as well. But have I shown you the data? Yes, and let me change that. You see the x-axis labels overlapping. That's actually bothering me. And so what we can do here is we'll set the x-axis major formatter. And this should be a date formatter. It actually depends on how pandas is going to truly, I actually set it up here, just a lowercase b to get the month abbreviations, and that should get us into good, perfect. So we have January through December, and you can see that this is revenue by region over months. I've shown you the data. Now what? This is what intentionality is all about. Whether you like it or not, I've actually facilitated one comparison over another. That comparison that I've made easier is the within month comparison. It's a little easier to look just at January. Try and ignore every other bar. Look just at January and then say, okay, north is blue, east is orange, south is green, west is red. South did the best in January. And while I've facilitated by accident this comparison, by facilitating this comparison, I've made it very hard to do a across month comparison or within a region comparison. It's very hard and very visually distracting. Try and follow all the orange bars from one month to another. All the visual competition that you get make those comparisons incredibly hard. And so what I always say is that if you're going to include some intentionality in your chart, if I'm going to tell you to focus on the within month comparison, we may as well do a good job about it. If we really want to prioritize that within month comparison, well, we should use another trick that we have. And we've seen this trick once before. It is the trick of small multiples. Now, instead of relying on color, which was incredibly visually distracting, I can splay out every single month into a chart unto its own And I can use position, again, another reliable channel, to tell you about the different regions. I no longer have to use color to encode that information. And what this does is it frees up my color channel to do something else. I can highlight the best or the most profitable or the highest gross revenue region within every single month. And what I can do is I can take this one step further by preserving the original colors and highlighting those colors. And what this does is here, south is green, north is blue, red is west, and orange is green. You can spend 3 seconds looking at this chart and you guys, south was leading in revenue generation for the majority of the months. And you could just do that quickly by just seeing that there's more green bars than there are any other color bars. So these are just some of the ways that we can use color to draw attention. We can use a layout of charts in order to reduce visual competition. And I'm forcing you, look at the within month comparisons. It's such an easy comparison to make. But I will say that sometimes we want to look at a different comparison. And when we do that, when we look at the opposite comparison, we might need to rely on a couple of other tricks. So if we want to see how data change over time, I'm going to show you a different data set here. And in this data set, I'm going to ask you a question. How many is too many? And so let's take a look at the data. It's, again, revenue over time, except instead of different regions, right, because there was only 4 regions, Northeast, South, and West, I want to show off the different sectors of my company. This is, I told you, it's a mega corporation. We have agriculture, we sell furniture, software, hardware, games, office supplies, cloud services, and cosmetics. And my boss gave me this data set, or maybe I just pulled it out of a table somewhere. And for my monthly report, I was told to visualize it. And so we'll go ahead and visualize these data. Great, they are on a plot. You're probably looking at this and you're wondering, what does each color represent? And to that, you'll have to look at the legend, then you'll have to look back at the chart, and you'll have to look at the legend again and back at the chart and at the legend again, and so on and so forth. And it's incredibly hard to just focus on a single department or a single sector and compare it to the others around it. And this is because we have just put too many things in this legend. We've tried to facilitate too many comparisons here. And as a result, we have this chart that facilitates this type of glancing behavior, and it quickly becomes overwhelming and overburdensome. And so, if you've ever heard something about the capacity of working memory in humans to be 7 plus or minus 2, I did study human memory in graduate school, and so I do have a leg to stand on here. We'll say 7 plus or minus 2 is for a digit span task. This is specifically for auditory working memory. So if somebody's talking about a chart and they bring up 7 plus or minus 2, it's absolutely wrong. You cannot hold 7 visual elements in your head and retain any degree of accurate information about them. Turns out there was work done in the early 2000s by Steve Luck to find the total number of visual elements you can hold in your head to be 4, about 4. Right, which isn't very high. Thankfully, there are some tricks. The first trick, well, I could use small multiples again, but we've seen that trick so many times, I don't want to show it to you again. Instead, what I'm going to do here is inline the labels that we saw earlier. And so, if I remove the legend and I just take the labels out of the legend and put them in the same color next to the line that they represent, I no longer have to do that glancing game. I can very easily see agriculture's blue, hardware's red, and I can make those comparisons incredibly readily because the labels are right next to the thing that they represent. So I don't have to do that back and forth game anymore. So inlining your labels, honestly, any chart where you have the ability to get rid of a legend, you're going to make that chart better. It's going to be less distracting, there's less glancing, there's less memory that you have to employ in order to actually understand what's going on. So that's just a couple of the tricks that we have to show you how you can redefine and revisualize your charts. Now, I will say, in this presentation, we saw about 1,400 lines of Matplotlib code. Yes, Matplotlib code is verbose, but like I said, it's the only tool in Python where you can actually do anything you want with a data visualization. And so to conclude and wrap up, I will say this. Regardless of whatever the tricks or tips that you use from today, always remember, A good dichotomy to go by for your data visualizations is to split them into those that are exploratory, which typically are ones that you just look at or maybe members of your team look at. They're quick, they're usually dirty, they don't have to be great, but their goal is to convey descriptive information, facilitate the exploration of relationships, uncover meaningful interactions, and as a caveat, I will say, don't overdo dimensionality. Although you can do things like small multiples or use facets, right? Looking at facets of every feature against every feature, if you have 80 features, I'm not going to look at an 80 by 80 grid of scatter plots and be able to make sense of it. There's just no way. So don't overdo the dimensionality, and remember the difference, the effective differences between our superimposition, overlaying two data sets or two groups onto the same chart or more, and juxtaposition, right? Laying them out next to each other. Then we also have our explanatory charts. This is the one where we want to really maximize that signal to noise ratio. We're picking out a message and we are justifying that message or that assertion that we're making. And so the two tricks that we have there, and if we think in terms of signal and noise, we can amplify the signal. And here we can put the bottom line up front, aka by having meaningful titles. We can use redundant encoding. Recode the metric that you want people to look at multiple different ways and really hit them over the head with it. You can guide attention. You saw me do this throughout the whole presentation. I use color specifically to make you look at certain points on certain charts. Additionally, you can use appropriate metrics and encoding, right? So this is your choice of metric. I didn't talk much about this one, but the idea is if you have some fairly complex data, you did a statistical analysis on it, you should not report that statistical analysis in terms of, let's pick something random, right? Slope coefficients or t-test, right? And you have t-values and p-values, or t-statistics and p-values. If my audience is a group of high schoolers, they're never going to understand, right, what it means to have a t-distribution of blah, blah, blah. However, if my audience are a bunch of scientists or statisticians, then I can know that I can use that metric and it's appropriate to use. So one thing that you should always consider is whom you are saying this message to. And finally, to, again, maximize that signal to noise ratio, we can minimize the noise. And to accomplish that, you want to avoid things like overplotting. You want to apply appropriate filtering or aggregation. You want to remove chart junk. And most importantly, in my opinion, you want to be intentional with your data visualizations. Thank you all for your time and listening to Data Visualization Concepts with Matplotlib. My name's Cameron Riddell, and if there's anything Matplotlib or data viz that you want to talk about, I'm more than happy to. Thanks, everyone.
Nicely done. All right, any questions for Mr. Riddell from the audience?
Well, I guess I have a comment. I mean, I think you've demonstrated clearly what we can do as far as we can go with standard Matplotlib. And by that, I mean no real enhancements. But are there people looking at real enhancements to visualization in Python? I guess I could call it Matplotlib++, which is, this would be very much a website or HTML based, but make them interactive. I don't know. I think there's probably a lot of useful things we can explore, but I don't know who's implementing it or standardizing it, because that's something to represent more cleanly higher dimensional data sets that enhance the explanatory nature of the stuff you were describing here. For instance, you know, for contour plots, maybe visualization within a multidimensional data set of here's maybe where 90% of the signal comes from, well, this contour plot, and it'll just illuminate that thing. I mean, that would be a practical improvement for my stuff, which is trying to interpret simulation output of, you know, simulated detectors and simulated sources. I don't know if
like a high number of inputs, features or inputs, and it's useful to maybe toggle through those through like a drop down or something like that.
Or yeah, some kind of click on the screen or click on this image or click on the contour in the image and it'll say, oh, okay, why did I choose these contours? Because they represent X, the top X or the bottom X% of the expected signal or the expected source.
So I'll say in terms of interactive data visualizations, Matplotlib absolutely can do it, right? You'll just need to embed the plots into a custom GUI, right? You can whip something up in tkinter. Now, I can't do it off the top of my head. It does require a little bit of Googling. That's where Matplotlib has you covered. If you want like a web interface, something like that, you can send static Matplotlib charts up to a web or up to an HTML front end. That's gonna get pretty clunky pretty quickly though. And so that's where you can use tools like Bokeh or Plotly to facilitate some of that exploration. If all if what you're looking for primarily is very quick exploration and kind of like exploratory widgets for free, definitely check out HVplot. It just takes a couple lines of code, and you can effectively say, here are like the dimensions that I want to explore, and you can, even if it's a continuous dimension, you can specify things like bins. If it's categorical, you get a free dropdown that lets you just toggle between those categorical values. And the pairing to HVplot would be hollow views. They're both made by the same group. HVplot is a specific implementation of, or a specific application of hollow views for pandas data frames and polars data frames as well. Although I don't think they actually integrate with polars. I think they just call two pandas before they do anything. So take that with what you will. But it is an incredibly convenient tool. So if you're exploring large swaths of high dimensional data, HVplot could be the thing that you're looking for. Or at least could be a neat thing to play around with for a few days before you say, this isn't the thing I'm looking for. That's at least what hollow views was for me in grad school.
I mean, I'll give my example is struggling with Matplotlib to do density plots as well as contour plots, and trying to figure out an appropriate color map to represent really the nature of the source and the detector fluxes that I'm seeing. I was supposed to get it done today, but I was sick this afternoon, so here I am.
Oh man. Well, I mean, I am of the opinion Matplotlib can do anything, but
yeah, it can.
It depends on the investment of time, right? For color maps, I don't know what the fluctuations you're referring to look like, or what their kind of periodicity or anything of the signal looks like. But if it sounds like they are continuous data, so you could use something if there's a lot of meaningful values in there. There's a normalized jet color palette called Rainbow that's pretty popular. And that could be useful for highlighting different bands of values if there could be multiple points of interest that you want to just look at. Then this would get into the cases, right, where just a simple sequential color palette isn't enough to explore the things you're interested in.
Quick question. I think with Plotly, there is a way that you can have an interactive plot, right, where you use your mouse and you can actually rotate. Is there a way to do that with Matplotlib? So
if you use the graphical user interface in Matplotlib, the default interactions are limited. And so let's see, I'll go ahead and share my screen again. So behind me, you'll see my screen. I'll hide here in the corner. Is that Anscombe's quartet example. And now every chart that you saw, right, I was executing live code and just using pyplot.show, which just runs a basic tkinter application. And you see I have a couple of widgets down here. And so these are just the basic predefined widgets or interactivity that you get with a Matplotlib chart. And so the most basic thing is I can actually move these X and Y axes. And since they are linked, they do move together. So if I move one of them, they all move. And then the other thing that you get for free effectively is the ability to zoom in on some points. And if you zoom in on one chart, it zooms in on all of them since I linked these axes. This is a very small stone throw in comparison to the types of interactions that you can get with Plotly or with Bokeh. I'm personally much more familiar with Bokeh. But you can do very advanced interactivity with those kind of newer charting tools.
Fantastic.
But yeah, and if like I said earlier, if you create your own GUI, I can share with you, if you email me, I can share my email in the chat. But I do have a talk where I did Matplotlib without PyPlot. And I effectively showed how to write the most bare bones tkinter application and how to embed a couple of your own widgets. Now, one thing I will say, writing your own GUI, it's not too hard, but then sharing that application with others can be a little bit more cumbersome. Whereas with the web-based stuff, you just host your own server, or you have your company host the server internally, and then all you need to do is just send somebody a link, and then they can play around with your dashboard. Whereas with a
Also,
graphical user interface, you have to send them the whole application, the whole source code.
actually, also, what about an HTML, just a single HTML file, or maybe the directory, where all the images are embedded? So you could send that as a zip archive, and it would be self-contained. It's not so much an abstract issue. I work a lot in very limited environments where you can't necessarily share a website. So does Bokeh do something like that, like convert it into an HTML directory with maybe not embedded images, but a self-contained HTML directory that can zip up and send off to people wherever?
Bokeh, I don't believe does that out of the box, but there's a really cool tool built on top of Bokeh called Panel, and that actually has the ability to do what you're speaking to. So effectively, Panel works quite well, or integrates quite. It's made by the same people who does the Hall of Views and HVplot, so all these tools work pretty well in tandem. But effectively, it can use the dimensions that Hall of Views gleans, and it can optionally, if they're continuous, it can sample them. And then as it samples all of the states of the different widgets or different interactions that you have built onto it, it just spits all those into a massive HTML file. I forget if it actually does a zip and then does any compression, but you can get a very massive HTML file in the end that you could send to someone, or you could put on Dropbox, whatever, and have them download and then open up.
So that example I brought up yesterday about Ash's Ash's principle. So you were accounting that as noise, right? But
that would have been social pressure, which is it's a little bit different from kind of noise in the traditional sense. But go on.
Right. So that's actually a different type of signal, right? Because it's coordinated.
For the social pressure?
For the social pressure.
Yeah, that would be a coordinated kind of impeding signal. Now, it's hard to tell if it's kind of a signal in the traditional sense, because it's biasing you towards one thing and not the other, whereas typically noise will be some type of equal distribution right around some value. But yeah, that would bias you to respond one way or another. And it does, I don't know if it's applications in terms of, looking at a chart, but I will say, if your boss tells you, hey, revenues are down, they show you a chart, and in your head, you're like, the revenues are not down, you might still agree with your boss just to be agreeable.
Right.
If your job's on the line or something like that. So social pressure is definitely a thing in decision-making, just overall, that we do have to compete with. But I don't know from a visual communication standpoint if there's much we can do from that.
So I would say that's a generalized problem. And I noticed that James did some quant work. When you have a coordinated effort, say like in moving stocks up and down, right? How can you identify that, and what's a good way to label that? Does that make sense?
Yeah, can you repeat that for me?
So in Ash's experiment, right, you have these confederates who are all acting in coordination, right? But you can also have that in say in financial transactions. You can have a bunch of different large players all acting at once, and and you see a effect in the market.
Yeah. So there's going to be social pressure in multiple different ways. One thing that I actually didn't talk about today was showing the context of your data, right? That's what I was doing with the one-to-many comparisons that you saw in the small multiples. But the bad thing that you can do is you can selectively pull context, meaning you can, just because my revenue is sitting at 10 million or hovering around there, I can make that look really good or really bad depending on the comparators that I bring in. So if I bring in other extremely large companies, it can make my revenue look tiny. But if I pull in, for context, a bunch of small companies, I can make my revenue look large. And so it is easy to mislead someone with a data visualization. And that would, I think, be kind of the comparison to social pressures. You can bias someone towards one conclusion over another just by inappropriately choosing what you put on the screen.
Yeah, and that's actually a specific technique. Is if you want people to feel that something is inexpensive, you keep mentioning high numbers first, right? Sales.
Yeah, a little bias. James, I see your hand up.
So I had a specific question about one of the examples you had, the first small multiples example, where you show the different plots next to each other. And it occurs to me as you bring that up that the most likely comparison somebody is going to make is a year-on-year comparison. They're going to compare 2000 against 2001, which means very likely they're going to want to compare 2003 against 2004, which suggests to me that the appropriate ordering here is a bootstraphodon ordering that wraps around, goes 2003, then below it 2004, then wraps around there to bring those closer. However, rather than litigate that specific point, I'm very curious. At what point do all of the tricks that you use to improve these visualizations go a little bit too far outside of what somebody's expectations are for like an Excel, the stupid Excel charts, and you start distracting them rather than encouraging them to look better at the data? At what point do all of these tricks kind of just don't do it, just stick with the thing that comes right out of the defaults because people are going to just wonder more about how you did that than what you're actually trying to show?
I'll say the threshold is if you look at your own chart and you're more impressed with how you did it rather than what the chart is saying, that's when you know maybe you did a little too much. But at the same time, if it does make a meaningful improvement, if that message is even more clear, like even this example, I think if my message is really daily customers increase across the years, then I should probably just put everything on a single axis and just highlight 1 year versus the other, right? With some type of, gray and white kind of stratified patterning. And that's undeniable. You'll just see the revenue just go up and up and up, and you don't have to worry about any of the ordering, right? Where 2003, you have to then read the next line. And so I think that could make it even more clear. And maybe the clearest of all would be to just take a summary statistic of each year and then a measurement of error. And then you just have something dead simple that anyone can look at. And so there's a lot of considerations. The one thing that I do like about this is you show all of the data. And so you reliably show the fluctuations as well here.
And James, I would point out that I'm sure you all know that this is very much domain specific. Like what works for maybe a realtor company might not work for people who work at CERN or even at the National Ignition Facility at Livermore Labs, where they're trying to interpret a lot of data at very high quality and visualize it in a way to do the executive summary of a lot of data. We don't know what's relevant or a lot of it's relevant, but in a way that, basically usefully guides decisions. And I envision that in practical terms. At that point, if people do a lot of that stuff, if they've got some stuff that they know they need for visualization, they just write some higher level modules that use Matplotlib at a low end to perform the visualization or the post processing and synthesis. But yeah, I know a lot of the plots I make in practice are, it looks very nice, but I find I'm still missing information that I need. And in a lot of use cases, I find I have to write custom code to just because I do it a lot of times. And I know the domain space well enough that, okay, I know here's just a few nods rather than the 80 that I would need to do when manipulating the lower level Matplotlib level for visualization and analysis. So yeah, but I do like these concepts, especially what I found useful is, the appropriate color map to represent things you need to focus on versus things you can ignore. And it seems to even work given, a lot of variation in the underlying nature of the experimental data or simulation output. Like for instance, something that's either basically uniform in the domain space or highly peaked. I find, choosing the right color map helps even over that big range of types of data, either simulation or experimental that I use.
Yeah, I think that's a great point, right? All of these domains work with extremely different data than one another. And a lot of these concepts can be applied to many in different ways. It's not a one size fits all, though. That's for sure. And James, I see your hand up again. Or was that from last time?
I have a related follow-up question. As I understand, Cameron, you're actually a very big name in popularizing open science. So this is more of an ethical question than it is a technical question. Clearly, when you're presenting the graph, it is important that you put your bottom line up front, as you said, to send your message, and you include enough information in the graph that somebody can make an adverse conclusion. So you put your point forward, but they can look at the data themselves and say, actually, you know what? I disagree. Your point's wrong. To what degree is it ethically necessary or responsible for you to allow them to make parallel conclusions that are not adverse to your conclusion, like, oh, but I also noticed something else? And to what degree is it more important to just eliminate that noise and let them focus on just one piece of the puzzle, just what I'm trying to say, but not all the other stuff?
I would say that if somebody can combat the message that you're using for a given data visualization, that means that they have probably some external knowledge, meaning they know that you cherry picked some selection or some comparison, and they know that what you're trying to present is a little bit skewed. Or it means that the assertion you made, whether it's in your title or any supporting text, is overgeneralized and is not directly or immediately supported by your data. That's why I said be very careful with the assertions that you make. It's just like if you're writing an academic paper or you just did a study, right? You don't want to overgeneralize your conclusion based on the results at hand. You should really only interpret that.
And there's a little bit of
that's a
politics
great point in the
that
chat.
too.
The first task is not to fool yourself. There's always, depending on what you're talking about, there's always going to be politics involved and biases going one way or the other. Absolutely.
Yep. I mean, I lean towards, be as honest as you can be as fair with the conclusions that you can make with the inputs that you have. And the chips will fall where they may. But if you work in a big organization with stakeholders who, for instance, might have an issue with whatever comes out, that's been my experience that, don't focus on this or leave this stuff out or, so.
Yeah. And I think that's a great point, Sam. James was referencing some of the work I do with open science. I work with NASA for doing open science training across the country. And one of the big things, whether you're sharing a visualization or you're sharing data, you're sharing results, is share as much as you can responsibly, right? And so a little bit relevant if you do human studies, right, and you collect a bunch of data, is that you can't just go sharing everyone's personal information. Additionally, if you work at a government research facility, you should be very sure that you consult your higher ups, your managers, to make sure whatever you're trying to share is shareable, right? And you're not breaking any laws or any regulations. So be as transparent as you are able to be. I see Oscar's hand up.
Gotta unmute, Oscar.
Oh, sorry about that. So Cameron, this is really, really educational for me. I work as a data analyst and mainly in Power BI. Excel, obviously the reporting tools like the regular reporting tools like SSRS but my question to you is, where can one like sign up for your course pretty much? Like where do you go to learn in depth the stuff that you just presented? Is it just the accumulation of all the the education you've had, or is there something that someone can, I'd love to like take some of the all the things that you covered in through some kind of course or something. This is awesome. So that's just my question. Take it
Of
off.
course. Well, thank you so much, Oscar. You can reach out to myself directly at cameron@dutc.io, and I can make sure that my team gets a look at that. I will say, if not just you yourself, but you also have a team that's interested in this type of training, we do team trainings in scientific computing, Python, and of course, data visualization. We do B2C sessions, so direct to consumer as well, which you can see, which we can let you know about if you reach out via email. Finally, as a couple of resources, as DN suggested in the chat, I will give you one of my favorite YouTube series, and I'll also give you a link to a couple of the talks I have given on Matplotlib. And I'll dig those up in the background. I'll paste them in the chat for you in a couple minutes. But I appreciate your kind words, Oscar.
You definitely have enough to publish your own books at this point.
Yeah, there's just data visualization ended up being a really deep dive for me, and it's been a fun topic and something that I have spent a lot of time learning about, especially once I found out there were textbooks on this topic. But James, I see your hand up as well.
If nobody else has any other questions, on the overplotting example that you showed, where you showed all the variations there, I was curious, you could possibly add some more fancy layout, like you could add on the x-axis or the y-axis, say like a density measurement, and you could even add an AVX line or an AHX line or some kind of envelope to identify the area with the most density. But my question is, at what point are you adding too much stuff to your plot? And it's just like, no. We don't need more bars. We don't need more lines. We don't need more stuff on the side. It's just too much. Keep it simple.
So I have if you all can see, I have the charts up behind me. What James is referring to is, yes, you can decorate the axes. This is often called using marginal distributions. And the idea is that I can plot like an orange and blue, density along the x-axis as well as an orange and blue density along the y-axis. That is a great way to help separate, right, the differences, the small differences along each of the axes. At what point is that just excessive and too much? I will say it's a great way at looking at how your data points interact, or if there's just an effect right along a singular axis. However, I will say that it should be evident by the data. For example, in these charts, you can see that the y-axis is a much better discriminator between our two groups rather than the x-axis, right? So whatever this dimension is, it's great. It's better at picking apart orange points or predicting, if this was some type of prediction model, at predicting orange versus blue. Whereas the x-axis, the horizontal, is not as good. And so do we need the marginal distributions to support that? It would, land the home run for the chart, I think, but I don't think it's going to change your life. I will say that if you're trying to make a chart for something you're trying to communicate, hitting someone over the head with your message is never a bad idea, unless you're doing it to the point where it's excessively misleading, right? And so that's the only caveat I would say. If you do it too much, people might think you're up to something.
Awesome. Well, thank you so much, Cameron. Excellent presentation.
Actually, there's like one last question.
Did we have another one? Should we ever do 3D plots?
Yeah. I don't know. I haven't seen a 3D plot that's been anything but confusing, or when it's not confusing, it's a surface region of 3D data. So, I don't know. I haven't found anything useful, but I'm maybe not the best judge of that.
Yeah, 3D
I-
pie chart. That's more like it'd be like a sphere, maybe.
Or you have a complicated shape, and you're going to say, what's the 1 kilovolts radiation temperature contour at this point in time? Those can be kind of useful. Or what's the highest density region in your imploding DT fusion capsule? Just to say, look how symmetric, asymmetric, squashed pathological things are when things bang. But beyond that, I don't know. And maybe that's good enough for, this is an example from my day-to-day, working with some of the folks at the laser facility at Livermore Labs. They have those, not just for managers visualizations, but actually, in design and review meetings to say, okay, here's what actually happened. How do we design an experiment to, take this information and improve upon it?
I've used a lot of 3D visualization for molecules and paths through molecules, but I usually don't do it in a plot. I do it in the tool that PyMol mainly for doing this.
Oh, okay, yeah.
So 3D data visualizations are very interesting. I will say if you have true three-dimensional data, yes, you can use a three-dimensional plot. Maybe just encoding that z-axis in color could be better. But I would say if you do both, you're not off to a bad start. The tricky part, or the part where it's obviously a no-go, is if you do like a 3D bar chart, it's the angle that you get, the perspective that you force onto the individual makes it incredibly hard to actually make judgments about differences in height along the axes that you're plotting against. And so I would say avoid 3D charts unless you really do have three-dimensional data that's an X, Y, and a Z. If you're just like if it's like PowerPoint circa 2002 and you create a bar chart and then you click 3D, absolutely don't do that. Actually, that's a blog post I've been wanting to do for a while, is how to create a silly 3D chart in Matplotlib.
Three D pie chart. What is the depth of a pie? What is the filling of your?
That's how many berries you get or filling.
All right. Well, we're approaching the end of the hour. Again, great presentation. Thank you so much, Cameron. And thanks to everyone for participating, especially James. You're the MVP of commenting and questions. Another good one. We'll see you guys all in a month. Next month is on the 11th, so it's actually the second Thursday of July, because if we had done it on the 1st, it'd be the 4th. And here in America, we don't really do much podcasting on the 4th.
Yeah.
All right.
Thanks so much to both Cameron and James for joining. Especially with all the resources that were in the comments.
Yeah, great stuff.
Indeed.
All right. Bye, everyone.
Okay.
Thanks,
Cheers.
everyone. See you
Bye.
around.
See you laters.